Data Analysis, Part 5, Probability and Statistical Inference. Hello everyone. Last time we nearly finished talking about design of experiments, in which we were trying to see why experiments can sometimes give you data in which the conclusions are difficult to determine or misleading, and how you can design experiments to make sure, as far as possible, you don't get such misleading situations. Here's a nice example from the recent literature. This is a plot which shows on the x-axis number of physicians per 1,000 population in a country, and on the y-axis confirmed COVID-19 deaths per million population in the country. This is observational data, and so it is vulnerable to the problem we looked at last time, Simpson's paradox. And you can see here the actual trend in the data is that the more physicians you have per population, apparently the higher the death rate. Clearly, this is not what one would expect if one had perfectly clean data. If all other things were equal between countries you were looking at, I am sure that having ample doctors per unit population would give you a lower death rate than having fewer doctors per unit population. Clearly what has happened here is that there is a second covarying factor in the observational data, which is, roughly speaking, prosperity. So, in fact, we are not just varying the number of physicians for otherwise equal countries. That would be an experiment which you couldn't really design, but that would give you clean data. In fact, what is happening is that the underlying truth is that countries have different levels of prosperity. Countries which have a high level of prosperity can afford and have more doctors per thousand population, but they also, partly because of that, and partly because of the general benefits of material wealth, these countries have populations which live much longer, so they have an older population which is intrinsically much more susceptible to death from infectious diseases. So that's how you get the total overall trend, is because of the confounding variable that prosperity causes there to be plenty of doctors, but also it causes populations to live long enough that they're susceptible to infectious diseases, outweighing slightly the effect of having more doctors. Nice example of confounding variables, which if you were shown this by someone very cynical, they might tell you, well, this is evidence that medicine makes people sick. Well, no, not really. It's actually a very clean example of a confounding variable. We looked at that last time, and what else did we say last time? We were designing experiments basically to minimize ambiguity that you can get of this sort, preferably, if possible, by doing prospective experiments in which you have randomized controlled trials, so that all other things where possible, apart from the one thing you're varying, do average out to be the same in each of the cases that you're looking at. In the previous slide of death rates and doctor densities, obviously the all other things included the prosperity of the country, which didn't average out to be the same, and couldn't because it's observational data. Okay, let's finish looking at some things to do with the design of experiments. So section 3.3, cause and effect. We just need to reiterate here the difficulty of attributing causation, when we have these observational studies. Just example 3.2.3a, something to discuss, just to show how this can lead to, this could lead you to quite worrying situations if you don't pay careful attention to where your data comes from. So this is a 1990 report. There was a study of 938 Medicare enrollees. It found that 345 owned pets and 593 did not. The people who did own pets had contact with doctors an average of 8.4 times in a year, whereas those with no pets had contact with their doctor an average of 9.5 times. These are retired people, Medicare enrollees. The study concluded that owning a pet improves the health of the elderly by relieving stress. that was the conclusion of the study. It would be lovely to believe this conclusion. It's almost certainly wrong. Certainly the conclusion is not convincing. It's actually very likely that we have here again a confounding variable. It may be that people who are in good health, or they enjoy a healthy outdoors lifestyle, these people are more likely to get a pet. That is to say, what's actually going on in the data is that people being in good health both means that they need to visit the doctor less often, and makes them more likely to own a pet. Not the other way round. Not necessarily that owning a pet improves their health. This could obviously lead to really bad advice. If you took the naive results of the study, you might recommend to people who are actually a bit too frail to safely own a pet that they get one, and you might actually cause more harm than good if you just naively take the result of this, interpreting this observational study. There are more things wrong with it than this. The investigator did not try to stratify or disaggregate the results by personality. Maybe it was just that people who are of a more anti-pet disposition, maybe they're also more pro-visiting the doctor, just as a matter of personality. We can't tell which is the case from looking at observational data. But you do have to be careful. Ideally, if you want to reach solid conclusions about medical data or industrial data, you want to be using a prospective randomized controlled trial, as we discussed last time, so that extraneous confounding variables don't co-vary with what you want to understand the effect of. But just be aware that, most of the time we are stuck with observational data and we have to make the most of that. Right, what else can we say? We mentioned the terms randomized and controlled trials last time, and we noted that this can only be done when you're designing an experiment in advance. If you want to learn a lot more about examples of people misinterpreting observational studies deliberately or accidentally, you could read this book, How to Lie with Statistics by Darrell Huff. This is not required reading for this course, because this book by Darrell Huff, it's actually, although it's the most popular university level or student book on statistics, it's completely non-mathematical. It's written by a journalist for journalists. It's an entertaining book because to a great deal of the time it teaches you statistics with the sort of sense that the author is trying to teach you how to be a pirate and to be dishonest. This is entertaining, but it's not really what he's encouraging you to do. He's really encouraging people to think carefully about the subject, think carefully about their sources of data, and work out very often simply where does the confounding variable come from in the observational data, which wouldn't be present if you had the ideal sort of designed experiment you would hope for in a scientific setting. Okay. Other than Simpson's paradox and confounding variables, a slightly related problem which you want to avoid when you design your experiment, or to be aware that it might happen if you're given data, is you need to avoid something called sampling bias. We'll have a look at a technical example of sampling bias in 3.4.1. No, but let's first of all just say in very simple terms what it is. Sampling bias is when, for example, it's a problem that you could get from a self-selecting sample of people. So, for example, if in a magazine survey some editor unwisely puts a coupon onto an adverts page, and the coupon asks the question, do you enjoy responding to surveys? If so, cut out this, and there's a yes-no tick box. If so, why not cut out this coupon, mail it to the magazine? And duly the next week, the editor opens up his post and finds out that 9 out of 10 of the coupons that have been sent back involve people ticking yes, they do enjoy replying to surveys. Okay, so you joke about, well, there's 1 out of 10 people don't enjoy replying to surveys, but they're really strongly motivated by doing stuff that annoys them, and they've sent back their coupon anyway. But of course, the editor would be very foolish to draw a conclusion about all the people who read his magazine. In fact, he's sampling from all the people who do send back replies to a survey written in a magazine, which is completely different from the population of all the magazine readers, about which you are much more likely to want to know conclusions. This is an extreme example of sampling bias, and it's a reason why some kinds of polls are completely useless. Online political surveys are fairly useless because you have the people who answer them. I'll give you data for that. They tend to be people who are unusually interested in politics. They're not particularly representative of the general population. Not without elaborate corrections, which are very arguable as to whether you can do them or not. Twitter surveys of the type retweet to agree, like to disagree. I don't think they're as common as they used to be, but they clearly have a designed sampling bias that retweeting is going to circulate to like-minded populations of people, or subpopulations within the general population, and it will do that more than the like to disagree will circulate to people who are inclined to disagree. So clearly, your retweet to agree, like to disagree surveys, they don't even recruit an audience which is representative of that particularly non-real-world population, that is the population of people on Twitter. Self-selecting samples are very bad because of sample bias. Sample bias can, however, also affect more scientific-seeming studies. So let's look at a slightly more technical case. 3.4.1, Parkinson's disease and country living. So a study reported higher rates of Parkinson's disease among people who live in rural areas. The study suggested a cause, exposure to chemicals in fertilizer. Now, in one way you can see this as a possible Simpson's paradox situation, but we could also describe it as sampling bias. In fact, you can see it two ways. We've looked before at the case of are there explanations for different results in rural areas to do with exposure to chemicals, agricultural chemicals. And it's not convincing because the populations are very different. So let's just look at this exact data again. So the study gives you a list of numbers, and it says the rates of Parkinson's disease are higher in rural counties than in presumably urban counties. So that's the result it got. Now let's consider how this conclusion can be, the numbers that you receive here may be affected not only by the true rates of Parkinson's disease in the rural versus the urban counties, but also to do with how efficiently these numbers are detected. So we have to remember, in all kinds of studies, it's very likely that there are different rates of some property, different rates of some outcome in two different situations, but you also not only have to have a different rate of some outcome, you also have to consider, are you detecting it equally efficiently in each situation? If you are, then you're avoiding sampling bias. But let's consider this case of Parkinson's disease. Bear in mind, you can't just find out magically what is the rate of Parkinson's disease in a county. It needs to these cases need to be diagnosed by medical doctors, and it is not easy to accurately adjust for the differing ability of medical doctors in different settings to diagnose diseases. It may be that the detection of Parkinson's disease in rural areas is simply more effective than in urban areas. Perhaps you can imagine reasons why. Maybe these are affluent areas with plenty of doctors per unit population. Maybe the doctors are less overworked than in some of these growing urban areas. So maybe the reason that you get a higher number of reports of Parkinson's disease is simply because there could be the same number, but they're detected more efficiently. You could also have a second reason for getting the higher reported numbers of Parkinson cases in the rural county without the danger actually being higher in these areas. So possible explanation too, people in cities tend to be poorer, this is where this study was taken, than people in rural areas. I think this is US data, and it is possible that being in poorer areas, the urban populations may have higher rates of death from various causes at most ages. And so a reason that the urban population might have a lower rate of Parkinson's disease is because the population is a younger age on average than the rural population. In fact, if you avoided sampling bias by doing something called stratification and measuring Parkinson's disease rates in groups of people of the same ages in the rural area compared to the urban area, you may find that there's no difference in the rates, in which case you might say, well, there's not an increased risk caused by the living in the rural areas. So in general, the same method that you would use to avoid Simpson's paradox might be usable to avoid selection bias if you could do an experiment, which you couldn't in this case, because there's no way you could assign people to spend their entire life for the benefit of a science experiment living either in a rural area or an urban area. That's not possible. But a laborious prospective randomized controlled study would be a way of looking for the influence of the setting, urban or rural, on health outcomes. It couldn't be done, and so you have to remember that when you're looking at this sort of the observational data on health outcomes, it's very likely there's selection bias, and you need to consider in this type of study population age and efficiency of medical diagnosis as well, in the case of diseases which you only learn about when they are diagnosed by medical doctors. Right. Section 3.4.2 is just a comment on the fact that people that you read about just because they have a fancy title or a doctorate, or especially a medical doctorate, don't necessarily assume they have a good understanding of how you should interpret data. So here's an example on how should one interpret, if one is trying to give the best advice possible, how should one interpret breast cancer survival rates and the effect, the possible benefit or not of mammography, of regular scans. So this is a newspaper column by some guy called Lawrence Lamb, medical doctor, and he recommended that a 42-year-old female letter writer should get mammograms. And this medical doctor, commented on two studies. So the first study was what I've been describing as a very good kind of study that gives clean data. It turns out he didn't think much of the results of this. He didn't rate this as highly as I would. The first study was a prospective randomized trial of 50,000 women, and patients were assigned at random either to receive regular mammograms or not, and the women were followed up for at least 7 years, and the incidence rate of breast cancer was measured. It turns out there was a slightly lower incidence of deaths from breast cancer in the group which did not receive mammography, although I believe it was lower but not significantly lower. There's an updated version, there's a link to an updated version of this study in the notes. and it's up to 80,000 women with the same result. No health benefit caused by being told or deciding to go and get mammograms regularly, as opposed to having normal contact with your doctor just whenever. And that's in this Canada study. So by comparison, by the way, and this is a huge study, and it's prospective. It was designed with a control group for no specific no treatment, but no automatic regular mammograms versus yes automatic regular scans. So this was designed to avoid all of the problems of observational studies, and it came out with the effect that sending people to get regular scans didn't cause any health benefit. By comparison, Lawrence Lamb put much more credence in a small retrospective observational study in which he found that he dug something up. In a retrospective observational study of women under the age of 50 who had breast cancer detected by mammography, 100 and so cases, or physical exam, because they've been to the doctor, 900-ish cases. The 5-year survival rates for women whose cancer was detected by mammography, he said, was 92%, compared to 74% for those cancers detected by physical exam. Alas. And he therefore said, well, clearly mammography is having a benefit. Well, that's not necessarily true. His advice might be correct, but if it's correct, it's coincidence. It's not justified by the data in the studies he cites. The big study, the first study, pretty conclusively proved no health benefit of regular mammography. The second study is therefore easily explained a different way. It could be that mammograms detect breast cancer sooner than physical exam, and so maybe the difference in 5-year survival rate after detection is simply that the women whose cancer was detected by physical exam had already lived longer with cancer than those in the other group. And this difference is not accounted for by simply measuring the 5-year survival rate. You can interpret that either as a kind of confounding variable or as a kind of sampling bias, and you can see how it's avoided by the big prospective randomized controlled trial. A second explanation is not all tumours are actually life-threatening, they're not going to actually affect your survival. It's possible that some small and non-dangerous tumours might have been found, or more of them might have been found by mammography than those found by physical exam. So maybe it was simply detecting less dangerous cancers, or in fact ones that wouldn't be a problem in any case. That would explain why the real respectable results from the big Canada study linked show that there's no health benefit caused there by regular scans for mammography to look for breast cancer. Now, just one final comment. While I say no health benefit caused by screening, that's not the same as no benefit at all, because somebody who goes for screening might simply find that they might actually have benefit simply learning more confidently about their health status. They might, even if they're having a scan and finding that they've got nothing wrong, they might actually benefit from that knowledge, even though the choice to go and have a scan, according to the big Canada study, doesn't necessarily cause any benefit in itself, and they would have been just as well off going for the alternative ordinary contact with their doctor as and when. Okay, so we've talked there about designing experiments. We've talked about the key rule. We want to minimize ambiguity or misinterpretation, and in general we want to have experiments where variations other than the choice of treatment or the factor we're looking at, there aren't any other things varying. We'd like the other things to average out to have no difference between the sets we're looking at where we are varying the one thing. If we can get that kind of study, then that minimizes the number of possible explanations for the data and gives us more certain conclusions. nonetheless, observational studies are what we're stuck with in most cases. They're valuable because we can often get large amounts of data at low cost. You just have to be aware that they are full of problems and hazards of interpretation, and we've discussed through plenty of them in this chapter. Great. So that brings us to chapter 4 on uncertainty and probability. This is the chapter where we'll start to look at mathematical methods for learning from data when the conclusions are uncertain. In other words, the fundamental task of why is there a subject called statistics, or why do we study data analysis? We've done the two foundation things which you need to know are done before we get to this mathematical probability chapter. You know how to do descriptive statistics. That's processing data and presenting it in a way that involves no uncertainty. And we've talked in chapter 3 about how you acquire data so that when we process it to learn about the wider world beyond the data we've just collected, when we do inferences, in other words, or when we make predictions about the future or about something we haven't yet seen, chapter 3 tells us how we collect data to be as informative as possible, and to we've talked about, in a qualitative sense, what is it that we need to avoid in order to not suffer from misinterpretations. In other words, qualitatively in chapter 3, how can we get data which is going to be as useful as possible? It's going to lead to conclusions which are as accurate as possible. In chapter 4, I'll stop talking so qualitatively, and I'll try to present the algebra of how we describe uncertain conclusions mathematically and precisely. Okay. Obviously, when we have a conclusion in which we are uncertain, we're going to say that we're going to give it a probability. You need to know that when you pick up a textbook on probability theory, it will probably tell you this, but it might choose one or the other. It will probably tell you that there are two mainstream interpretations of what probability means. First, probability might mean a degree of belief that some statement is true. Jumping ahead, I might say that my degree of belief that somebody's birthday, I haven't met them before, somebody's birthday is tomorrow, my degree of belief in that, I might give it a probability of 1 in 365. That's an example of degree of belief probability. Now, my degree of belief probability that a person's birthday is tomorrow is a number that I can compute from the information that I possess. For somebody else who knows this person well, they would either have a degree of belief, they would know when their birthday is, and they'd either have a degree of belief of 1 because they'd know it's tomorrow, or 0 because they'd know it's not. You see, different people, depending on the information that you've collected so far, can have a different degree of belief probability in some statement. A second interpretation of probability is the long-run frequency at which an event occurs. This should feel a bit different. In other words, in the case of you meet somebody and is their birthday tomorrow, well, you might say there's a sort of physical rate constant, which will turn out to be 1 in 365. That's how often does it turn out that the person you've met, their birthday is tomorrow. That feels like a different concept, although clearly these are somewhat related. In fact, it will turn out that whichever of these two main interpretations of probability we want to adopt, we can use them to write down the same set of laws of mathematical probability. Because we write down the same laws from each of them, we get a concept called probability, which obeys some mathematics, which is the same. And to that, because probability behaves in the same way mathematically, regardless of which interpretation you believe is actually the case. The interpretations can stand in for each other. It might feel a bit odd for them to stand in for each other. For example, in the case of is somebody's birthday tomorrow, you might think, like me, that the most natural way of interpreting my probability is, yes, it's a function, it's a degree of belief. It's best described as summing up the information that I have about the situation. The idea that you have a sort of physical property of people that are arriving in your presence in the form of some sort of a randomized experiment, and they arrive with a rate constant of, on average, 1 in 365 of them have a birthday tomorrow. You might think that's a slightly odd way of looking at that particular example. On the other hand, thinking about physical rate constants for things arriving turns out to be a good way to talk about some probabilistic physics like radioactive decay, and in those cases, long-run frequency is a good model for what we think is really happening. But as I said, you can use degree of belief probability or long-run frequency. You can sort of make them stand in for each other. And the fact that you might prefer one or the other in to explain the reality of a situation, that's fine, but just bear in mind you're going to get the same mathematics regardless of which you choose. And that means that some people who want to be perverse can always choose the unnatural description for some situation. And if they want to think of people turning up and their birthday tomorrow being described by some sort of random physical process, they can follow that interpretation. It's just a bit harder. So there are those two views of probability. In this course, we're going to go with probability as a degree of belief. In other words, it's a property of the information we've received. Great. So let's say more about this. 4.1, my degree of belief as probability, or we could also call this subject logical probability. I gave you at the start of this course some statements about which we might be uncertain. For example, given the data, you meet a nice couple from a town called Lake Wobegon in Minnesota. We might want to describe our degree of certainty in the conclusion. Most couples from this town are nice. Now, 4.1a, a definition, a probability in this system, it's a subjective assessment about whether an event in question will occur or has occurred, or whether a statement is true. Now, 4.1b, an important fact about this is that in order to quantify whether some statement is true or whether an event will occur, we need a scale, just like we would for any other measurement. It will turn out that in probability theory, the scale is something that we can define by means of a calibration experiment, which might be an imaginary experiment. A calibration experiment is one where all of the outcomes are equally plausible for the observer. So in order to take my actual example statement, are most couples from the town of Lake Wobegon nice? I can answer this if I can come up with some answer like the probability of this statement being true is equal to the probability of rolling 3, 4, 5, or 6 on a fair die. That will turn out to be, that's going to be a good way of writing my conclusion. Obviously for this exact one, it turns out I'm going to be writing this as down as a number, which would be 2/3 or 0.66 recurring. And we want to know, how do we compute these probabilities, either for a calibration experiment or for some statement in the real world? Well, in order to compute probabilities, we first of all need some notation of probabilities. This is going to be section 4.3. And we'll need some mathematical rules for probability theory, which will be section 4.4. So, mathematical notation of probability. This is worth my reading out, or it's worth, you need to know this. So pay attention when you read the notes. Do read this section carefully. So we refer to the probability of something, or that something is true. The something is called an event, and the notation capital P of, in brackets, A, has the same meaning as the sentence, the probability of event A being true or taking place. So the building blocks of events are called outcomes in probability theory. Outcomes are mutually exclusive results, meaning only one will occur in each repeat of an experiment. Outcomes are also things that we have no need to divide any further. So, for example, consider rolling an imaginary six-sided die, which has labels 1 to 6. Everyone understands the outcome as the number on the top surface when the die stops rolling. In this situation, it's an imaginary situation. We have no need to further subdivide these outcomes by, well, we roll a 1 and it's raining outside, or we roll a 1 and it's sunny outside. No need to do that. We stop subdividing at the point where it's obvious we can safely stop subdividing the outcomes. Some notation. So, 4.3a. Rolling the number 1 is an outcome. It also could be called an event, which you would call, in curly brackets, 1. Rolling an odd number is also an event, and it's more than one outcome. We could describe the event as in curly brackets 1, 3, 5. You might want to have a bet. Probability theory is quite important if you want to do betting. You could have a bet on not rolling a 6, which you would describe as not 6 in words, or mathematically as a tilde 6, swirly line 6. This would be the set of outcomes in curly brackets 1, 2, 3, 4, 5. You need to know that there's the term called the union of events, which includes the outcomes which are in either or both events. So, for example, the union of rolling a 1 and 2 with 3 is 1, 2, 3. Labels of outcomes which are in both events are not repeated. So the union of 4 or 5 with 5 or 6 is simply 4, 5, 6. The way you remember this, so union, the union operator, think of it as like forming the United States of America. So if, when the United States of America was formed, it was formed by the union of, let's say, some imaginary confederations. Imagine you have the Atlantic Federation, which had Florida and New York, and it also had the Caribbean Trade League, which had Florida and Texas. Well, if you form the union of those, you don't get a magical second copy of Florida. And the same thing is how the union operator works in probability. You just get the list of all the outcomes, but you don't get extra copies of any outcome. That would be silly. The largest possible event that you need to worry about is called U in algebra, or just universe in words. In rolling a die, as above, you write down the universe as just in curly brackets 1, 2, 3, 4, 5, 6. We always, in probability theory, we have models of the real world, so you don't need to worry about other outcomes like the dog comes along and eats the die. You just have to remember that because probability theory is about models of the real world, if you do get data that was outside of your universe, you realise you have to stop and adjust your theory in order to deal with the data you've just received. In most cases, hopefully, there won't be any uncertainty about what belongs in your universe of outcomes. And in rolling the die, it's as written in there in 4.3e. The smallest possible event is called the empty set. It's empty, it contains no outcomes, and it's just written phi, or there would be nothing in between the curly brackets. So there are some bits of notation of probability. You might need to manipulate those in simple ways in this course, and you'll need to know this is how people manipulate them if you read some textbooks on probability theory. Right. Those are definitions in section 4.3. Section 4.4, what are the quote-unquote mathematical properties of probability theory? In section 4.4, here are three mathematical properties of probability, which you might also find called by various different names. You might find them called the laws of probability. You might find them called the Kolmogorov axioms. The Kolmogorov system of probability is one particular probability theory. You might find these laws of probability obtained from another system other than the Kolmogorov system of probability. For example, you might find the Definiti system of probability, which is a good Bayesian system. You would also in that system find these laws. And you would in fact find a fourth law, which I'll come to shortly, which Definiti says you simply have to take as a starting point. Now these laws of probability, I'm just going to call these the laws of probability, 4.4a to c. Where do these come from? So the answer can be as hard as you like. One answer is that you could get these in a philosophically sound way. You could say, as I've been saying, probability is my degree of belief in some statement being true, and you could, I wouldn't recommend this because this is really hard, you could buy a book by Richard Coxs on Cox's Theorem, which says that if your degree of belief has to obey certain philosophical properties, if you have certain statements which you think in plain English must be true about a degree of belief, for example, that a degree of belief is a physical property of the information that I have available, and therefore, regardless of the order in which I consider my information, as long as I consider all of it properly, I should get the same degree of belief. So if you believe that property, and some other nice properties, you can follow through his algebra, and you will find that these laws of probability must apply to what you've called degree of belief probability. So you can read Cox's theorem and get these laws of probability in a philosophically pretty sound way. But you don't need to. For this course, you are very welcome to take these laws of probability as intuitively correct things. So we'll look at them, and hopefully you will say, yes, these are things that I'm very happy with these mathematical laws applying to probability, which is going to be measuring my degree of belief in a statement. Okay, so 4.4a, the probability of an event is a non-negative real number. That's going to be fine. I'm going to be very happy describing a probability of something as, for example, 0.7, that something is true. And let's look at the following laws. So 4.4b, if the universe is the largest event, the probability of one of a comprehensive list of outcomes happening, I'll call 1. So that means my probability, it's going to be a number between 0 and 1. And I've no problem with that. 0 is going to be intuitively, that's a statement which is false. 1 is going to be a statement which I'm certain is true. And clearly I'm going to have some 0.7 or some other number, intermediate numbers, to describe partial certainty in something. And 4.4c, the third law of probability, is to do with adding up the probabilities of events which have no outcomes in common. So if events A and B have no outcomes in common, then it turns out I simply have to, if we're doing this intuitively, I hope it will make intuitive sense that the probability of the union of A and B, that's one of the outcomes happening which is within those events which had no overlap, is simply the probability of A plus the probability of B. Hopefully, you can take these laws of probability as intuitively acceptable statements. about probability theory. If you must take them as philosophically sound, then you can get them from Cox's theorem. But let's add one more additional comment on top of this. These are just mathematical laws, and you will notice, if you look at them again, that the laws of probability, they don't only describe degree of belief. In fact, a particularly important thing which the same laws describe is if I go out into the car park with some coloured chalk and I draw some overlapping shapes in different colours, it turns out that the laws of probability, as written here, equally validly describe the behaviour of areas of overlapping coloured chalk circles. That is to say, first law, the area of any shape that I draw is greater than or equal to 0. If I've not drawn a shape, that's 0. Anything else has some area. The largest event has the area equal to the entire car park. The largest thing I can draw has the area equal to the entire car park. We call that an area of 1. And other things within that obviously have a smaller area between 0 and 1 car park of area. And if I have non-overlapping chalk outlines, then I can say their combined area, or the area of the union of those shapes, is equal to the sum of the individual areas. Why do I flag this up? Well, it's a fluke that laws which we want to use to describe degree of belief happen to be the same as the laws which one would write down for describing the areas of chalk outlines. Now, because you would write down the same laws for them, that means that sometimes you can work out a probability relation by considering overlapping areas, because the same mathematics is obeyed. But it's important to think of it this way, that it's a fluke the same laws are obeyed, hence some results are the same, rather than doing it the reverse way around that some bad, naughty textbooks do. Some naughty textbooks suggest, here's a rectangle and we've got some overlapping circles, and they appeal to you to say, well, clearly the behaviour of probability is the same as the behaviour of these overlapping areas in this, they would call it a Venn diagram. Actually, you can't just start and say, here's a diagram of overlapping areas. By the way, probability behaves the same way. Actually, what you have to do is rigorously justify that probability obeys these laws, 4.4a to c, and that overlapping areas in a car park obey the same laws. Therefore, you can actually get, you can understand some relations in probability by considering overlapping areas. But that's a fluke of the fact that those are two physical phenomena which happen to obey the same laws, and it's not because there's anything mystical about area which defines the way probability has to work in the real world. Certainly, it doesn't define the way that degree of belief needs to work in the real world. Okay. If that was too philosophical, don't worry. Important thing, the laws of probability in section 4.4, you can take as simply intuitively correct descriptions of how my degree of belief should behave in some statements or events. Using the maths that we've looked at there, you can get some further relations for some other definitions. So you can read through the maths for the probability of event A will, by taking those laws of probability and the definitions, is simply 1 minus the probability of not A. And considering that again, since the probability of the universe, the probability of one of a comprehensive set of outcomes happening is defined as 1 in the second law of probability, that means the probability of the empty set phi is 0. Okay. And there's a little bit more to read. Some problems, as I said, in overinterpretation of data occur because the investigator has not included within their universe some things that can actually possibly happen. And if those things turn up, then that will cause problems for your analysis. Okay, great. Now, we want to use these laws of probability in order to learn about. So given some data which have arrived, so given some events have occurred, we want to make conclusions about the probability of some other events. Or in other words, we want to work out the probability of a prediction or an inference. In order to do this, we will use probability notation for something called joint probability of two events, so that we're able to write down a system that has the data that one event is the data that we've received, and another event is the uncertain conclusion which we want to learn about. We will look in part 6 at the notation of joint probability and then conditional probability. That's going to be the useful thing. Given some data, we know which event has happened, or we have received some information. What does that tell us about the conditional probability? In other words, how does that change our degree of certainty in some conclusion, a prediction about the future, or a conclusion about some physical reality? So we'll look at that and Bayes' rule and how to start applying that in part 6.